So, to continue on with the second half of this unit, will sort of be all the other miscellaneous stuff that didn't really fit with the first half. I try to separate this into two groups. So what we talked about for the past 2 weeks were systems of linear equations, solving simultaneous equations. And when we did that, we saw that our answers are either a single point, no solution, or infinitely many solution. Today, 3.6 is talking about doing the same thing, but except instead of using equations, we have inequalities. Now, how does that change our thought process? When it comes to solving equations, we have techniques to do it. We have elimination, we have substitution, because the answer was either a single point, or no solution, or it was the line itself. Well, when it comes to inequalities, the answer is always infinitely many solution. It's that shading of the half plane. So there really isn't a substitution way to do this. There really isn't a elimination way to do this. When it comes to systems of linear inequalities, graphing is the only way to go. And I know that sounds like, oh, that's a big chore. I don't like graphing. I hate graphing. But it actually makes things a lot simpler because your answer is a visual answer rather than listing them out. So what's the idea? Well, recall the idea of solving systems. And the idea was as follows. Solutions to systems are points that are common to all equations. Right. If we were solving two equation systems, it was common points between two equations. It could be common points between three equations, four equations, so on and so forth. So if I change equations into inequalities, it should be the same idea. My answer should be common points. But again, since inequalities solution sets are half planes, they will be rather common shading points. So for today, the idea is this. Solutions to systems of inequalities will be common shading. What does that mean, common shading? Picture's worth 1,000 words. I think if we do an example, it'll make crystal clear sense. Okay. So, for example, suppose I ask you to solve y is strictly greater than negative 2x minus 5, and y is less than or equal to x plus 3. So again, the idea is for this lesson, everything is by graphing. So I'll go ahead and draw a coordinate grid. Right? There really is no elimination or substitution with these problems. Your only bet is graphing. So draw tick marks. I'm not sure how big this should be. Maybe a 10 by 10. And in case we forgot how to graph, let's do a quick review of graphing. So I'll do the top inequality in blue and the bottom inequality in this yellow color here. Yeah, you guys can see that. So the first thing I want to do is make sure it's in slope-intercept form, which both of them are. So to graph a linear equation or inequality, you start with this last number. So this last number is negative 5. So I know my y-intercept is at negative 5. So I'll make a point there. 1, 2, 3, 4, 5. And then you just listen to your slope. In this case, my slope is negative 2. I always like to think of slope as a fraction. So that's negative 2 over 1, which tells me I need to go down 2 because he's negative and write 1. Or I can go up 2 and left 1. When it comes to inequalities, there's two types of lines, solid or dotted, and all it depends on your inequality. Since your inequality is strictly greater than, there is no line underneath it, it will be a dotted line. So I'll go ahead and take a straight edge and then just connect the dots with a dotted line. Okay. The dotted line is to indicate that all the points on the boundary, all the points on this line are not included in the solution. Now this was the idea from, I think that was Unit 1, all the way back into Chapter 1. Solutions to inequalities are half planes. They're literally shade half the page. But which page you shade, all you have to do is read the inequality here. This inequality says greater than, so greater than you typically think of up. So I'll shade upwards. Now, I have the luxury of technology and I can erase easily and I can shade and whatnot. If I was a student personally, I don't want my paper to get messy. What I would do is just like draw upward arrows as a reminder of where I'm going to shade, right? Because I don't want my paper to get messy. So I'm just going to draw upward arrows to remind me. Then I'll just repeat the process with the yellow graph, right? So start with +3 because that's the y-intercept for the yellow graph. +3 here. And then listen to my slope. My slope is 1. So that tells you go up 1, over 1, up 1, over 1. Or if I want to go backwards, down 1, left 1, down 1, left 1. Take a look at the inequality. Since there is a line underneath it, since there is or equals to, it will be a solid line. So I'll grab my straight edge and then just connect the dots with the solid line. For his shading, I read the inequality. It says less than, so less than makes me think of down. So I'll go ahead and shade downwards. And again, I'm just going to draw arrows to remind myself where to shade because I don't want my paper to get messy. Now, I'll go ahead and shade for real on my page because I have digital paper, but I would save it, the final shading on your own paper. So I'm only doing this for emphasis. So the idea is this. I'm only going to show the answer to the blue. You don't have to copy this in your paper. This is the answer region of the blue. I'm going to show the answer region to the yellow. This is the answer region to the yellow. The idea is solutions to systems of inequalities. I know it's very bright, so I'll delete that. Solutions to systems of inequalities is where they both shade. And I hope everyone can see that they both shade in this region. So that is what I would actually put on my paper. I would put this guy here as my solution. Every single one of those points in that region is the solution set, which is why when we're solving systems of linear inequalities, our answer is an actual graph rather than a list because it's impossible to list this out. There's an infinite amount of answers. That's it. Easy peasy. Any questions with this example? Question?
So, if this asking for like, when you define the y-intercepts or the x-intercepts, for that, since you have it shaded, would you put infinite many solutions?
So the question was, for this particular answer, would my answer be infinitely many solutions? No, I would not write that down. I would actually, my answer is the picture itself. This is what I would be grading. Do you have the two lines? Do you have the right dotted and solid lines? And do you have the correct overall shading? So those are the three components I'm looking for.
So that's all the work we have to do?
This is what you would submit to me. Yep. So that's basically the idea of today's lesson. Pretty simple. The question is, hey, Mr. Vo, how can it get harder? It really can't. I mean, I guess the only way it could be harder is if the equations aren't in slope-intercept form.
So
go ahead.
If they're not in slope-intercept form,
You just make it into slope-intercept form. Yeah. So I mean, I guess this is quote harder. Suppose I ask you to solve 2x plus 3y is less than 6. And y is greater than or equal to -2/3 x plus 4. Oh no, Mr. Vo, one of the inequalities is not slope-intercept form. All you got to do is just put it in slope-intercept form. So before I graph this, I'll go ahead and do slope-intercept form. So I'll take this inequality here. 2x plus 3y is less than 6. And then I'm going to solve for y. Let's subtract 2x from both sides. And then last step is to divide out the 3. So I get y is less than, 3 doesn't go into negative 2 evenly, so leave it as a fraction. Negative 2 over 3x plus 2. Okay. Give me a second. Now, I actually do want to graph this, even though the idea is very simple, because I sort of want to show you a special case when it comes to inequalities. So again, let's label these. I'll call this, I don't know, the blue graph, and I'll call this the yellow graph. Right. So it's both equations are in slope-intercept form, so you just go ahead and graph this guy. This looks good. Let's move him down here. I'm going to move this guy over to give myself some room. There we go. All right. So, make your tick marks. So let's graph it. Graphing the blue function, we have a y-intercept of 2 and a slope of negative 2/3, which tells me I need to go down 2 and right 3, or up 2 and left 3. The inequality is strictly less than, so he'll be a dotted line. Let's do the yellow graph. The y-intercept is a 4. Oh, I got to do the shading. I forgot to do the shading. So for the blue graph, he's strictly less than. Less than makes me think of down. So I'm going to shade down. Now for the yellow graph, the y-intercept is 4 and the slope is negative 2/3. So go down 2, right 3, or up 2 and left 3. And then you can connect the dots. Since this inequality is or equals to, you're going to do a solid line. Hey, they're parallel. And then we do the shading. So since it's greater than, we shade up. Right. Right. So the solution set is where they both overlap. So if for the blue function, you shade downwards, for the yellow function, you shade upwards, will those two colors ever touch? No. So the answer to this question would not be this picture. The answer would be no solution. That's what I would submit. So it is possible to get no solution even with inequalities. It's if you have parallel lines and they do not overlap each other. The question was, is there a way to get infinitely many solutions? Well, remember that a regular inequality already has infinitely many solutions. So technically, the previous example is infinitely many solutions. I just wouldn't write out infinitely many because the answer is the actual picture itself.
So that scribble area, that's the answer.
So yeah, so this scribble area is all the solutions to this problem. Yep. So the only time you'd have to write something out is if it's no solution. Yep. But good question. So the observation was, oh, this is easy. They have the same slopes. They're parallel. Not all parallel systems of inequalities will be no solution, though. It all depends on the shading. Yeah. Last but not least, again, okay, Mr. Vo, you made it harder, but that really wasn't harder. How can you make it really, really hard? Well, the only way I can make it even more challenging, which, spoiler alert, it isn't challenging at all, is if I toss an absolute value in there. Say, for example, solve y is less than or equal to 3, and y is greater than absolute value of x plus 4. Now, you cannot do this unless you know what the shape of an absolute value function is. So let's see if we can remember from Unit 2. You guys remember when you graph an absolute value, what shape it produces? It produces a V shape. Think of function transformations, up, down, left, right. What does a +4 tell you to do inside with the x? Left 4. So I highly suggest, if it's on the outside, it goes up. I highly suggest we take a look at, I forget what it was, 2.6, 2.7. We need to know those function transformations. So then let's go ahead and sketch this guy. So let's do the easier one. The top function I'll call blue. The bottom function I'll call yellow. So the blue function is just a constant function. Y is less than or equal to 3. So we know that y equals equations will always be a flat horizontal line. And because he is or equals to, it'll be a solid line. So I know that for the first equation, it's just a horizontal line at y equals 3. Right? Since the inequality is less than, I know I'm going to have to shade downwards. Okay. Let's do the yellow function. Again, we expect this to be a V, but there's function transformations. I have to go left 4. So instead of starting at the origin, I'm going to go left 4. 1, 2, 3, 4. That is my starting point. How do I make the V? I have to look at my quote slope. My slope will be this number here. You don't see it, so it's a 1. So you go up 1 over 1. Up 1 over 1, up 1 over 1. But since it's supposed to be a V, you do it in the other direction. Up 1 over 1, up 1 over 1. You look at the inequality. It's strictly greater than, so it'll be a dotted line. And since the inequality is greater, we think of shading up. So you shade up. So hopefully we can see that our final answer should be this inner triangle here. That would be the answer to the system.
What if it's just one vertical line?
The question was, what if it's just one vertical line? So something like shade down, and then you shade to the left, say, for example.
Yeah.
Well, where do they both overlap? They both overlap here. Yeah, in that quadrant. Yeah. No. So systems of inequalities, it's very straightforward. The only way we can solve it is by graphing. So you graph everything on the same coordinate plane. Your final answer is where they overlap. Hey, Mr. Vo, how can you make this even super, super, super hard? I don't know. Maybe I can give you 3 inequalities, 4 inequalities, 5 inequalities. It really doesn't matter. The idea is the same. To solve systems of inequalities, graph them together. Your answer is the overlap. Okie dokie? That is it. That is 3.6.